Hi, welcome to the second video for the solution of past paper of Edexcel IAL Physics Unit 1 Gen 2017. In the previous video, we saw solution of some all the MCQs and question 11 and question 12. In this video, we will start solution from question number 13. So let's start. Question number 13. A ball is dropped and reaches the ground after 0.42 seconds. The ball bounces and is caught at the same height from which it was dropped. Draw on a graph paper below the velocity time graph for the motion of the ball. You may assume that the time the collision with the ground takes and all friction force is negligible. Show you're working in the space provided. Okay, so the situation is it's all about the motion of bouncing ball. That means you have a ball that okay, and then you drop the ball, you have some ground, so the ball is falling down, remember, because it is dropped, so initial velocity of the ball must be 0, and when the ball comes down it hit the floor and then bounce back and it goes up, and then according to condition the ball is caught at the same height. Same height means there's no energy loss. Okay, so we need to plot velocity and time graph. That means we need to find a velocity at the time of bounce. That means this is v. Um, it's a question mark that we need to find. So in order to find v, I'm going to use equation u is u plus at is equal to v. So you can say that this implies, because initial velocity is 0, so final velocity v is equal to 0 plus 9.81 times time, and time is 0.42, so 0.42. When you solve this, you have v is equal to 4.12 meter second inverse. Okay, so this is the velocity when the ball is bouncing or reaching the ground. So what do we need to do? We need to mention this velocity on the graph. Okay, so you can take some point here, and this is, so you can say that this is your positive velocity 4.12, and then this is your negative velocity 4.12. Why do we need positive and negative? Because it's all about velocity time graph, and uh, velocity is changing, coming down and going up, so direction changing, so we need to mention both uh, velocities as well as time of the bounce on the time axis. So we need to mention somewhere according to the region or interval or scale. I need we are going to mention the time 0.42 somewhere, and the time when the ball is caught again, and this time, because no energy loss, and this time it would be double of this time, so somewhere here we would have 0.84, and then we um, are going to sketch our graph. So that's how we do that. Remember, uh, the final velocity at the time of bounce is 4.1. So this is your positive velocity 4.1, and this is your negative velocity 4.1 in meter second inverse. and these are the time of bounce and time when the ball was caught. And then because the ball is starting from rest, so graph must start from origin. This is the first graph. That means the ball is coming down, falling, 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 and at that time, that means 0.42, it is the time when the ball is just hit the ground, and it's about to bounce. So remember, the ball is coming down, so velocity is increasing, but in opposite direction or in a negative direction. When hit, you have a sudden increase due to impulse of the floor, and then this region is showing that ball is going up and the velocity is decreasing, 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 and it is caught there. So this is how you draw your graph. There is one important thing in this question, that in my graph I assume that when the ball or some object is moving down, I took this direction as negative, and the positive direction I took, oh sorry, I'm sorry about that, and upward direction I took positive. So according to my sign convention, this is my negative direction, and that this is my positive direction. But if someone, or if you choose the other way around, meaning if you say, okay, if you took downward motion as positive, that means upward motion must be negative. So your graph looks like this. I'm sorry about, because I'll try it. Let's see. Okay, and then yes, this one, and then, so this red line will be your graph if you choose this. Okay, so both are acceptable. I hope you understood. Okay, let's say question number 14. The manufacture of a glassware requires high temperature. Hot glass can be drawn into thin strands to be used in optical fibers. Explain in terms of properties of the glass why this technique requires a high temperature. Okay, it's properties of the glass, and it's all about the glass. So you can say that glass at normal temperature or low temperature, glass is a brittle material. Okay, that means it will go a very little deformation, or almost no deformation if some forces are applied, or it will shatter if forces deforming forces is increased. But high temperature high temperature causes viscosity to decrease. If viscosity to decrease, then glass becomes ductile. Be careful, I'm using the word ductile here because I looked at a thin strand. That means glass is converting into thin strand. That means glass is making in the form of wire, so the glass becomes ductile. That's why we need high temperature. So glass, initially low temperature glass is brittle, and high temperature requires, because we need thin strands, so it becomes then ductile, and you can uh, form shape whatever you want. So you can write all these things in a sentence. At normal temperature, glass is brittle, that is, it undergoes very little or no deformation. High temperature causes viscosity to decrease and glass becomes ductile and undergoes a large plastic deformation, so easily can be drawn into wire, or if you wish, you can write a thin strand. Yeah. Okay, so let's see question number 14. B. The technique of glass blowing allows hot glass to be manipulated into a variety of shapes. The graph shows the variation of viscosity with the temperature of for glass. Uh, explain why high temperature are required for this technique. Okay, so if you see the graph, it's clearly it is showing inverse behavior or inverse relation between temperature and the viscosity. That means you can say that viscosity is inversely proportional to the temperature. So viscosity is inversely proportional to the temperature. That means if you increase the temperature, viscosity is going to decrease. So if viscosity is going to decrease, that means rate of flow is going to increase. And remember, these are typical statements that we generally we often write in relation of viscosity and temperature. So listen carefully. Whenever these types of reasoning question comes, be careful. You need to relate viscosity with the temperature. So viscosity is inversely proportional to the temperature. So the viscosity is decrease and rate of flow is increase. And then you can add whatever you want to add, depends on the question. But these three uh, points that you should mention. But in this, it's 2 mark. So it's sufficient to say that is inversely proportional and viscosity decrease, so rate of flow is increase. Uh, that's how you can write. Okay, question number 15. A skydiver jumped out of a plane and fell for 50 seconds before opening his parachute. The graph shows how the skydiver's velocity varied with the time over the first 50 seconds of his jump. Okay, this is 50 seconds, so this is the total time graph, and it's all about, basically in this graph we have a three region to understand. If you start from origin and somewhere here, like these point, if you say here, it's not, but we can assume that it's a straight line. So for this line, velocity is increasing almost at with a constant rate, but after this time velocity is still increasing, but the rate of increase in the velocity is decreasing, and the time comes when the increase in the velocity is no more and velocity becomes constant. So listen again. For the first interval, you need to give the reason that the velocity is increased with the constant rate. In the second interval, velocity is still increasing, but the rate of increase has decreased. And after this point, velocity is constant. And if you recall, this region is called a terminal velocity. So how would you explain these? I'm sorry. How would you explain these three regions? So when a skydiver, this is just a point where the skydiver is jumping. Let's say it is a plane. When a diver jumps, at that moment, the only force acting on the diver is the weight, and there is no resistance at that moment. So for a very short interval, divers falls with the acceleration equal to g, and this is the time when the divers keeps accelerating with the constant rate and the velocity increasing. And this is the first interval. But after falling some distance or after a very little time, weight is still there, but aerodynamic drag or drag starts acting, air drag or aerodynamic drag in opposite direction. And remember, drag depends on the velocity. So this is the time when the net force, which is still in the downward direction, but net force has decreased because of the increase in the drag force. So after this moment, as diver keeps coming or keeps falling down, so the drag force keeps increasing, and somewhere when drag and the weight becomes equal, so W is equal to D. This is the time where all forces acting on the diver is balanced, and net force or resultant force, net force is zero, and the diver keeps falling down with a constant velocity, and this is the third region. Okay, so that's how you can write all the point. See if you can understand. Initially, as drag force is zero, the skydivers accelerate with g. The velocity of the divers increases as he falls due to increase in the velocity. Air drag keeps increasing and net force keeps decreasing until drag equals the weight. And at this point, net force becomes zero, so the divers keeps falling with a constant velocity called the terminal velocity. Okay, part B. Sketch on the graph above the motion of the skydiver after he opens his parachute. So this is the graph, and you need to sketch the diver after opening. Okay, fine, opening the parachute. So after 50 seconds, if diver opens his parachute, then drag force increases dramatically. That causes to velocity to decrease with very some new value, and then after this it keeps falling again with some constant velocity. So make sure that you draw this um, horizontal line. It should be a horizontal. Okay, so this is called a second terminal velocity. Okay, part CI. Explain the effect of the mass of the skydivers on the terminal velocity reached before he opened his parachute. So effect of mass is, of course, so mass, because remember, when diver is coming down, so weight is acting and aerodynamic drag is acting. These two forces are acting when diver is coming down. That means because mass is in effect of mass. Okay, fine. And due to mass, weight is going to change. So suppose if you increase the mass, that will cause weight to increase because W is equal to mg. W equal to mg. If you increase the mass, then weight is going to increase. So to balance the weight, a large amount of drag will be needed to balance. That means diver will take more time to reach the terminal velocity. So terminal velocity would be higher. So if mass is higher, then terminal velocity would be higher. So mass of the diver is increased, then greater drag force is required. to balance or cancel the weight effect, the driver will take more time and reach terminal velocity. Okay, that means terminal velocity would be higher. Next, okay, explain how the skydiver could decrease his terminal velocity as he falls. So if you need to decrease the terminal velocity, that means a diver should take less time to reach the terminal velocity, and less time means drag force should be higher. So in order to increase the drag force, so drag force need to increase. Why is that? Because you need to decrease the terminal velocity. That means uh, you must take less time to reach, or to attain, or to reach the terminal velocity. Okay, so if you need to increase the drag force, the major factor during dive is a surface area. So if you increase the surface area, that will cause to increase in the drag. That means diver will take less time to reach, so terminal velocity would be decreased. So in order to decrease the terminal velocity, the diver can increase the surface area, due to which drag force will increase, and diver takes less time to reach the terminal velocity. Part D, the skydiver's jumps was being filmed by another skydiver. Both skydivers jumped out of the plane at the same time. During the period of filming, only the skydivers who was being recorded opened his parachute. When viewing the recording after the jump, it appeared as though the skydiver being filmed moved upward as he opened his parachute. Explain this apparent movement. It's quite clear, because suppose you have two diver, and of course, so this is diver 1 and this is diver 2. Diver 1 is the one who's being filmed, and the diver 2 is filming. So diver 1 opens the parachute. So open the parachute cause drag force increasing the drag force for diver 1. So due to dramatic increase in the drag force, velocity of the diver 1 decreases. But the diver 2 who's filming the event or jump, the diver 2 keeps falling with the same or previous terminal velocity, that which should be higher than the new velocity of this. That's why the diver 1 appears to move upward. So that's how you can explain all these statements, and these are my wording. You can rephrase in your sentences, so it's fine, but you must understand the concept. Okay, thank you very much for this session. I hope you enjoyed, and we will see the rest of the question in the third video, and I will try to finish rest of the, I guess, question. Whatever the question 3 or 4 or maybe 2 are there. So in the next part. See you then. Thank you.